Never rely on obscurity alone. Opening, the secret that everyone knows. There is a particular flavor of confidence that security through obscurity produces, and it is more dangerous than most other forms of false confidence precisely because it feels so reasonable. The administrator who has moved SSH from port 22 to port 47823 knows, with genuine satisfaction, that the automated scanners hitting the internet will not find it on the expected port. They're correct about that. Automated scanners targeting port 22 will not find the service. What they have not fully examined is the question of what happens when a scanner targets all 65,535 ports, which is not a hypothetical. It is a standard technique that takes minutes, or when the service's existence is disclosed through a log entry, a certificate transparency record, a browser history artifact, or a conversation with a former employee who knew the port number. The protection was real for exactly as long as the secret remained secret. The moment the secret leaked, the protection vanished because there was no protection underneath it. This is the core failure mode of obscurity as a primary security control. It is not that obscurity provides nothing. It does provide something. Friction for unsophisticated attackers, noise reduction in automated scanning logs, a delay in the reconnaissance phase of an attack. These are genuine, if modest, benefits. The failure mode is treating that friction as a substitute for authentication, authorization, encryption, and access control rather than as a thin additional layer on top of them. When an attacker defeats the obscurity, and the historical record of how long hidden things stay hidden is not encouraging, they should encounter a system that is still secure. If the obscurity was the security, the system is now open. Kerckhoffs's principle, formulated by the Dutch cryptographer Auguste Kerckhoffs in 1883, states this with a precision that has not aged. A cryptographic system should be secure even if everything about the system, except the key, is public knowledge. The security of the system must reside in the key, the secret, not in the algorithm or the mechanism. In modern practice, this principle extends far beyond cryptography. It is a design philosophy. Build systems that remain secure when an attacker knows exactly how they work, and ensure that the only thing the attacker lacks is something that is genuinely hard to obtain. Not a URL, not a port number, not a naming convention, but a cryptographic credential or an authentication factor that cannot be guessed, leaked without detection, or reconstructed from observable system behavior. This session works through what that principle demands in practice, at the design level, in the specific tools that enforce real security versus decorative obscurity, in the failure modes that emerge when the principle is violated, and in the role-specific moments where the difference between obscurity and security determines whether an organization is actually protected or merely comfortable. The foundation, Kerckhoffs's principle, open design, and what real security requires. The vocabulary surrounding this principle requires some care, because the word obscurity is used in two different ways in security discussions, and conflating them produces confused thinking about what is and is not acceptable. The first use is obscurity as a primary security control. The system is protected because the attacker does not know how it works or where it is. The hidden admin panel. The API endpoint with an unguessable path. The custom encryption algorithm whose design is not published. The internal network IP range that is not documented. In each of these cases, the protection exists only as long as the secret exists. If the attacker learns the admin panel's location, the API endpoint's path, the encryption algorithm's design, or the internal IP range, the protection is gone. There is nothing underneath it. The second use is obscurity as a supplementary layer on top of real security controls. The system is protected by authentication, encryption, and access control, and additionally the attacker does not know the system's design. In this case, the obscurity adds friction. The attacker must first invest effort in reconnaissance before they can attempt to exploit vulnerabilities. But the system remains secure even if that reconnaissance succeeds. This is the legitimate role of obscurity, and it is the role that Kerckhoffs's principle does not prohibit. What it prohibits is the first use. What it endorses is designing systems such that the second use is the worst case, not the best case. Open design is the principle that flows directly from this. A system designed in the open, where the architecture, the protocols, the algorithms, and the mechanisms are all publicly documented and scrutinized, benefits from a form of security validation that a proprietary, hidden system cannot access. When AES was selected as the advanced encryption standard by the National Institute of Standards and Technology, the selection process was public. The algorithm was published. Cryptographers worldwide analyzed it, attempted to break it, published their findings, and the algorithm was evaluated against those findings before being standardized. This process is the reason that AES is trusted. Not because its design is secret, but because its design has been subjected to the most adversarial scrutiny that the global cryptographic community can apply, and it has held. A custom encryption algorithm designed in secret by a small team does not benefit from that scrutiny. Its security is unknown. It may be strong, or it may contain a subtle flaw that its designers did not recognize. And the only way to know is to expose it to adversarial analysis. This is why the distinction between the algorithm and the key is so fundamental. The algorithm's job is to transform plain text into ciphertext in a way that makes the transformation computationally irreversible without the key. The key's job is to be the actual secret, the thing that must remain unknown to the attacker. A system where both the algorithm and the key are secret is more fragile than a system where only the key is secret, because secrets do not scale reliably. The algorithm's design may be discovered by a researcher, by a disgruntled employee, by a patent filing, or by reverse engineering the binary that implements it. The key, if it is a properly generated cryptographic key, cannot be discovered by any of these means. It must be obtained directly through theft, interception, or brute force. Building the security on the key rather than on the algorithm's secrecy means that the security degrades gracefully when the algorithm becomes known, rather than catastrophically. The same logic applies outside cryptography. A symmetric encryption scheme like AES 256 derives its security entirely from the 256-bit key. The algorithm is fully public. Any attacker who intercepts a ciphertext and knows the algorithm, which any competent attacker will, cannot recover the plaintext without the key. An asymmetric scheme like RSA derives its security from the computational difficulty of factoring the product of two large primes, and the public key is, as the name implies, public. The private key is the secret. In neither case does the security depend on the attacker not knowing how the mathematics works. It depends on the attacker not possessing a specific, well-managed secret. NAT, Network Address Translation, is worth examining in this context because it is one of the most frequently misunderstood security controls in common infrastructure. NAT translates private internal IP addresses to a single public IP address for outbound connections and performs the reverse translation for inbound connections that match established outbound sessions. It was designed to conserve public IPv4 address space, not to provide security. The security benefit it appears to provide is that internal IP addresses are not directly reachable from the internet. Inbound connections cannot be initiated to a private IP address because the private address is not visible outside the network. This is real as far as it goes, but it is obscurity, not access control. An attacker who establishes a foothold inside the network through a phishing email, a compromised web application, or a supply chain attack is now inside the NAT boundary and can reach internal addresses directly. The NAT provides no protection for east-west traffic. It provides no authentication for the traffic it does translate. It provides no encryption. It provides no protection against an outbound connection initiated by malware on an internal host. Organizations that treat NAT as a security control rather than an address conservation mechanism that incidentally creates some inbound connection filtering are relying on obscurity to protect a network that has no east-west controls underneath it. The structural tension, the cost of secrecy, and the value of scrutiny. The tension that makes this principle genuinely difficult to apply is that obscurity feels like security. When an administrator changes SSH from port 22 to a high-numbered port and the automated scanning noise in the logs drops by 90%, the change feels effective. When a company's internal admin portal is placed at a URL that nobody outside the company knows, it feels like the portal is protected. The feeling is not entirely wrong. These changes do reduce certain kinds of surface-level activity. The problem is that the feeling of protection is not calibrated to the actual protection provided, and when those two diverge, decisions are made on the basis of false confidence. The cost of secrecy as a security strategy manifests in several ways that practitioners who have relied on obscurity recognize from experience. The first is the cost of maintaining the secret. A secret that is known to one person has a low probability of leaking. A secret that is known to a team of 20 people has a higher probability. A secret that is known to everyone who has ever worked in a department, including people who have since left, has a probability that approaches certainty over a long enough horizon. The hidden admin URL that the IT team has used for 3 years has been accessed from dozens of browsers, stored in bookmarks, included in internal documentation, sent in emails, and seen by contractors, auditors, and former employees. The notion that this URL remains obscure is a fiction sustained by the absence of visible compromise, not by actual secrecy. The second cost is the false sense of completeness. An organization that has deployed a hidden URL for its admin portal and considers the portal secure has a mental model of the portal's security that is wrong. When a security review recommends MFA and IP allow listing, the response is often that the portal is already secure because the URL is hidden. The obscurity is actively preventing the deployment of real security controls by creating the impression that real security controls are unnecessary. The third cost is the asymmetry between the defender and the attacker. The defender must keep the secret indefinitely across every person who knows it, every system it is stored in, and every communication in which it appears. The attacker needs to learn the secret once. This asymmetry is not manageable at scale. Real security controls, properly implemented authentication, encryption, and access control do not have this asymmetry. If an attacker learns how EES works, they are no closer to decrypting a ciphertext encrypted with a key they do not possess. The defender does not need to keep the algorithm secret. They only need to keep the key secret, and the key is a specific, manageable artifact rather than a piece of organizational knowledge distributed across dozens of people and systems. The value of scrutiny, the opposing side of this tension, is the benefit that open design provides. A cryptographic algorithm that has been analyzed by thousands of cryptographers and has withstood that analysis is more trustworthy than one that has not been analyzed at all. A security architecture that has been threat modeled, penetration tested, and reviewed by external parties is more trustworthy than one that has been kept confidential on the grounds that an attacker who does not know its design cannot attack it. The scrutiny is the security validation. The confidentiality is the avoidance of validation, which means the design may contain flaws that will only be discovered when an attacker finds them. Architecture: what real security looks like when obscurity is stripped away. When you strip away the obscurity from a system and ask what remains, you find out whether the system was actually secure. This is not a thought experiment. It is the premise of a well-run penetration test. The penetration test is typically scoped with the assumption that the tester knows the system's architecture, has access to the source code in a white box engagement, or can discover the system's configuration through reconnaissance. The tester is given, or can discover, the information that the organization assumed an attacker would not have. What the penetration test reveals is whether the security that the organization believed it had is actually present underneath the obscurity. A web application architecture that is genuinely secure when the attacker knows its design has several properties that obscurity-dependent designs typically lack. Authentication is enforced at every access boundary, not assumed at the perimeter. Authorization checks whether the authenticated user has the right to perform the specific action they are attempting, not just whether they are authenticated. Input validation is performed server-side, independent of client-side controls that an attacker can bypass by modifying their request. Encryption protects sensitive data at rest and in transit regardless of whether the attacker knows where the data is stored or how it is transmitted. Logging records enough information about every access and every action that a post-incident investigation can reconstruct what happened even if the attacker attempted to cover their tracks. These properties are not improved by adding obscurity on top of them. They are improved by testing them against an informed adversary, which is what a penetration test with a white box scope provides. A system that is secure against an informed adversary is secure. A system that is only secure against an uninformed adversary is secure until the adversary becomes informed, which is a matter of when, not if. The hardening of a Linux server illustrates this distinction concretely. When a security team hardens a server, they perform a set of actions that could be divided into two categories. The first category is obscurity actions, removing version banners from web server responses, renaming default accounts, changing default ports, suppressing error messages that would reveal internal implementation details. These actions reduce the information available to an attacker during reconnaissance. They are not without value, but they are not what makes the server secure. The second category is real security actions, disabling unnecessary services, removing unneeded software, enforcing strong authentication for all access, applying the principle of least privilege to every account and process, enabling host-based firewall rules that restrict inbound access to the specific ports and sources that are legitimately needed, configuring audit logging to capture the events that matter for incident investigation, and applying all available security patches. These actions make the server secure regardless of what an attacker knows about its configuration. A server with only the first category of actions is an insecure server that is slightly harder to find. A server with both categories is a secure server that is also slightly harder to find. The distinction between these two categories of action is the operational expression of Kirchhoff's principle. Design the security such that the second category is what protects the system. Use the first category as friction on top of that protection, not as a substitute for it. Tools that enforce real security versus decorative obscurity. 4 tools illustrate the principle by showing the specific way in which each one is frequently deployed as obscurity when its security value comes from somewhere else entirely. SSH is the tool most frequently subjected to port obscurity thinking. The standard deployment of SSH on port 22 makes it a target for automated scanning and brute force credential attacks. Moving SSH to a non-standard high port, 47823, 58921, any port that is not 22, reduces the automated attack noise in the log significantly. This is the benefit that gets cited, and it is real. What does not change is the actual security of the SSH service. If the service is configured to accept password authentication, it is vulnerable to credential stuffing and brute force regardless of which port runs on. An attacker who discovers the port through a full port scan, through a network traffic capture on a compromised internal host, through a configuration file exposed in a public repository, through a former employee, is now facing the same password authentication that was always the real attack surface. The security of SSH comes from key-based authentication, from disabling password authentication entirely, from restricting access to specific source addresses where operationally feasible, and from MFA for privileged access to critical systems. These controls make the SSH service secure on port 22. Moving it to a different port makes it quieter, but not more secure. The correct deployment uses both real security controls for the actual protection and the port move as a minor additional friction that reduces noise. Encryption makes the distinction between the algorithm and the key so visible that it is the cleanest possible illustration of the principle. When an organization uses a standard, publicly documented encryption algorithm, AES 256 for symmetric encryption, RSA or elliptic curve cryptography for asymmetric encryption, and manages the keys correctly, the encryption is secure even though any attacker who intercepts the ciphertext knows exactly what algorithm was used to produce it. The security is entirely in the key. When an organization instead uses a custom proprietary algorithm on the grounds that an attacker who does not know the algorithm cannot break the encryption, they are relying entirely on secrecy of the algorithm. This approach has 2 failure modes. The first is that the algorithm may be discovered through reverse engineering or disclosure, and once discovered, it may be trivially broken if it was designed without the benefit of cryptographic expertise and adversarial scrutiny. The second is that even without discovering the algorithm, a cryptanalyst applying statistical analysis to a large enough sample of ciphertext may be able to identify weaknesses in the algorithm without knowing its design. Properly implemented AES is resistant to both of these attacks. A custom algorithm is resistant to neither with any confidence. Hidden SIDs in wireless networking represent obscurity applied to a layer where the friction it provides is minimal and the operational cost is meaningful. Broadcasting and SSID, the network name that appears in the list of available wireless networks, is a convenience for clients that need to connect. Suppressing the broadcast hides the network name from casual users. It does not hide the network from any attacker with a wireless analysis tool. The SSID appears in probe request frames from clients that have previously connected and are looking for the network, in beacon frames when clients are nearby, and in the raw 802.11 traffic that any monitor mode capture will reveal. The effort required to discover a hidden SSID is measured in seconds for anyone with a wireless adapter in monitor mode. The real security for a wireless network comes from WPA3, enterprise with 802.1x authentication. Each client authenticates individually using their corporate credentials. The authentication is handled by a radius server, and a compromised set of credentials cannot be used by a device that does not have the correct client certificate. This architecture is secure against an attacker who knows the SSID, who knows the authentication protocol, and who knows the network's architecture. A hidden SSID on a WPA2 PSK network with a weak passphrase provides the illusion of security while the underlying authentication mechanism remains trivially breakable. A WEF deployed as a virtual patch represents the most nuanced case, because a WEF can serve both as a genuine security control and as an obscurity mechanism, depending on how it is understood and positioned. When a critical vulnerability is discovered in a web application and a patch is not yet available from a vendor, a WEF rule that blocks exploit patterns for that vulnerability is a legitimate compensating control. It buys time. It reduces the attack surface while the underlying vulnerability exists. It is not a substitute for the patch. When the patch is available, it should be applied because the WEF rule may be bypassable and because the WEF adds operational complexity that the patch eliminates. Where the WEF becomes an obscurity mechanism rather than a security control is when it is treated as a permanent solution. When the vulnerability is known, a WEF rule exists, and the patch is never applied because the WEF handles it. The WEF in this configuration is hiding the vulnerability rather than addressing it. The attacker who discovers the WEF bypass through testing different payload encodings, through a zero-day bypass in the WEF itself, through a direct connection that bypasses the WEF, will find the original vulnerability still present, still exploitable, still unpatched. The real security is the patch. The WEF is a temporary shield, and treating a temporary shield as a permanent fortification is a specific instance of relying on obscurity. Implementation. Applying the principle at 3 layers. 3 implementation scenarios demonstrate what the principle demands in practice, in the network layer, in application security, and in server hardening. And in each case, the same structure appears. First, understand what the obscurity provides, then build the real security underneath it, then use the obscurity as a supplementary friction layer with no delusions about what it is. Implementing NAT on a border router is the standard network address translation deployment that hides internal IP addresses from the internet. The implementation involves configuring the router to translate all outbound connections from internal private addresses to the single public IP, and to maintain a state table of these translations so that return traffic can be correctly routed back to the originating internal host. Port forwarding rules can be configured for specific internal servers that need to be reachable from the internet. A web server, a mail server, by forwarding traffic received on the public IP at a specific port to the corresponding internal address and port. The security analysis of this configuration is as follows. The NAT translation hides internal addresses from external visibility. This is obscurity. An attacker cannot directly initiate connections to internal hosts because the internal addresses are not routable from the internet. It also filters unsolicited inbound connections because the state table only permits inbound traffic that corresponds to an established outbound connection. This is a real, if limited, access control property. It prevents external hosts from connecting to arbitrary internal ports. What it does not provide is authentication of the outbound traffic, encryption of any traffic, prevention of outbound connections initiated by malware on internal hosts, protection against any east-west attack that originates from an already compromised internal host, or access control for the specifically forwarded ports beyond the port forwarding rule itself. The implementation that takes NAT seriously as a partial defense rather than a complete one combines it with a host-based firewall on every internal system, network segmentation that limits what internal hosts can reach each other, encrypted communications for all sensitive data, and authentication at every service boundary. NAT becomes one layer in a defense in-depth stack rather than the outer wall of a perimeter-based architecture that has nothing behind it. Implementing secure password storage is the application layer embodiment of the principle. The obscurity failure mode in password storage is storing passwords in a reversible or weakly protected form on the grounds that the attacker would need to access the database to exploit it, and if they have accessed the database, the game is already over. This reasoning conflates the cost of database access with the cost of password recovery. A database breach that exposes a password list in plain text or in a weakly hash format allows the attacker to recover credentials that are valid across many other services. Credential reuse is the rule, not the exception, and to persist in the compromised environment even after the breach is discovered and the database is secured. The correct implementation uses a password hashing function specifically designed for this purpose, BCRYPT, Argon2, or SCRYPT. These functions are deliberately slow. Their computational cost can be tuned, which makes brute force and dictionary attacks against the hash computationally expensive at any scale. Assault, a random value generated per user, is concatenated with the password before hashing, which ensures that two users with the same password produce different hash values and prevents pre-computed rainbow table attacks. A pepper, a secret value stored separately from the database, an application configuration, or a secrets manager, is optionally applied as an additional layer so that an attacker who obtains the database contents but not the application configuration cannot begin cracking the hashes at all. The security in this design is entirely in the algorithm's computational cost and the salt's uniqueness. The algorithm itself is public. The fact that BCRYPT is being used is not secret and does not need to be. The attacker who knows the hash, the salt, and the algorithm used to generate them still cannot recover the password more efficiently than the hash function's computational cost allows. This is Kirchhoff's principle applied to password storage. The security is in the algorithm's properties, specifically its resistance to efficient inversion, not in concealing which algorithm was used. Hardening a Linux server produces a specific illustration of the two categories of action. The obscurity category includes suppressing the SSH banner that advertises the server's OS and SSH version, disabling HTTP server tokens that reveal the web server software and version and response headers, and configuring error pages to display generic messages rather than stack traces or internal path information. These actions reduce the reconnaissance value of interacting with the server. The real security category includes disabling root login over SSH, enforcing key-based authentication, and disabling password authentication, removing all packages that are not required for the server's intended function, configuring the host-based firewall to accept connections only on the specific ports needed and only from the specific sources that are legitimately permitted, enabling and configuring audit to record authentication events, privilege escalation events, and file system changes, in sensitive directories, and applying available security patches on the schedule defined by the Vulnerability Management Program. The first category makes the server harder to fingerprint. The second category makes the server resistant to attack even by an attacker who has fully fingerprinted it. Both are applied. Neither is treated as a substitute for the other. When obscurity fails, 3 scenarios from the alert queue and the lab. 3 failure scenarios show what happens when obscurity is either the primary defense or when an attacker's obscurity blinds the defender to what is happening in their own environment. The first scenario is the VPN that remote users cannot connect to after a configuration change. The symptom is a flood of help desk calls reporting that remote access is broken. The error message indicates the network connection was interrupted. The recent change history shows that the VPN gateway was reconfigured to listen on a non-standard port. The security team's decision to reduce scanning noise. The diagnostic process begins with the client side. The VPN client is configured with the gateway address and a port. If the port was changed on the gateway, but the client configuration was not updated, either because the update was not pushed through the MDM or because a subset of clients are running a version of the VPN software that caches port configuration, then the client is attempting to connect to the old port, which is no longer listening. Verify by checking the gateway's listening ports against the port configured in a failing client's VPN settings. If they do not match, the remediation is a client configuration update, which should be tested on a subset of clients before being pushed broadly. If the ports match and connections are still failing, the diagnostic moves to the network path. A port change on the gateway requires that the new port be permitted through every firewall between the client and the gateway. The client-side firewall, any intermediate network devices on the corporate network, and the gateway-side firewall or security group. If the gateway is in a cloud environment, the security group likely needs to be updated to permit inbound connections on the new port. If the gateway is on premises, both the internal firewall and any upstream carrier-level filtering need to be verified. Check the gateway's connection logs for whether the connection attempts are arriving at the gateway at all. If they are not, the block is upstream. If they are arriving and being rejected, the block is in the gateway's own configuration. The lesson this troubleshooting scenario teaches is that the port change, the obscurity measure, created an operational failure that required a diagnostic process to resolve. None of that complexity improved the security of the VPN. The VPN security comes from the cryptographic tunnel it establishes, the authentication required to establish that tunnel, and the access controls applied to traffic inside the tunnel. Moving the listening port changed none of those properties. It added administrative complexity and a failure mode that the real security controls do not have. The second scenario is the malware sample that returns zero detections when submitted to a multi-engine scanning service, but contains strings that are obviously suspicious on manual inspection. References to common system directories, function names associated with command and control communication, patterns consistent with download and execute behavior. The analyst who submitted the sample is trying to determine whether this is an undetected threat or a false alarm. The zero detection result from automated scanning is itself a signal about the attacker's technique rather than a signal about the sample's safety. The malware author has applied obscurity to defeat signature-based detection. The common mechanisms are packing, compressing, or encrypting the binary with a packer that is itself benign, so that the malicious code is not present in the binary in a recognizable form until runtime. Encoding, transforming the malicious strings using XOR, base64, or a custom cipher, so that the signature patterns that detection engines look for are not present in the raw binary. And polymorphism, where the binary's own code is modified on each generation while its behavior remains constant. The analysis approach for a sample exhibiting these characteristics begins with entropy analysis of the binary sections. A legitimately compiled binary typically has code sections with moderate entropy and data sections with lower entropy. A section with very high entropy, approaching the maximum of 8 bits per byte, is often compressed or encrypted, which is characteristic of a packed binary. A packer identification tool can attempt to identify the specific packer used and, if it is a known packer, unpack the binary for further analysis. If the packer is unknown or custom, dynamic analysis, executing the sample in an instrumented sandbox and observing its behavior at runtime, can capture the unpacked code as it is loaded into memory for execution. The Y-ray rule that was detecting an earlier variant of this malware and now fails to detect the modified version is likely matching on a string that the obfuscation has transformed. The resilience fix is to write rules that target behavioral indicators that are harder to obfuscate. Not the specific string value, but the pattern of operations the malware performs. Not the encoded payload, but the decoding routine that must be present regardless of what it decodes. An attacker can trivially change the XOR key, which changes every encoded byte in the binary. They cannot easily change the loop that reads encoded bytes, applies the XOR operation, and writes decoded bytes to a target address, because that loop is the functional mechanism of the decoding. Targeting the mechanism rather than its current output is a detection strategy that is robust to trivial obfuscation changes. The third scenario is the detection rule for base64, encoded commands that generates 100 times its normal alert volume overnight. The analyst receiving this alert spike must determine whether a real attack campaign is producing legitimate detections at scale. A change in the honeypot or production environment has attracted a new category of scanner, or there's a bug in the rule logic that is producing false positives at scale. The first diagnostic step is to examine a sample of the alerts rather than treating the volume as the signal. Pull 20 alerts from the spike period and look at the content of the base 64, encoded commands that triggered them. If the decoded content is consistently a specific pattern, a specific downloader command, a specific C2 callback, a specific payload format, the spike is likely real activity, a campaign using base 64, encoded commands at scale. If the decoded content is varied and largely benign, legitimate administrative scripts, encoded configuration blobs, encoded data payloads are not commands. The spike is likely a false positive condition where benign activity is being flagged by the rule. The false positive investigation asks what changed in the environment at the time the spike began. A new deployment, a new tool being evaluated, a scheduled job that runs nightly and encodes its parameters, a legitimate automation script that was recently updated to past configuration as base 64. Any of these could be the source. The rule logic that was correctly scoped for the previous environment may now be overly broad for the current environment. The remediation is a suppression rule for the specific source, encoding pattern, or command format that is generating false positives, combined with validation that the suppression does not also suppress genuine attacker activity with similar characteristics. The underlying lesson of this scenario is that obscurity, specifically attackers using base 64 encoding to obscure their command from casual inspection, creates a detection challenge for the defender that the defender must navigate carefully. Base 64 is used by both attackers and legitimate administrators for entirely different purposes. The rule that detects attacker use of base 64 will also fire on legitimate administrative use unless it is scoped with additional context. The source process, the destination, the frequency, the decoded contents characteristics. Context is what transforms a noisy rule into a high-fidelity detection. And context is what the attacker's use of obscurity attempts to defeat, by making their commands look similar enough to legitimate activity that context-free detection fails. 3 roles, 3 encounters with the line between obscurity and security. The security architect, the detection engineer, and the threat researcher each encounter this principle at a fundamentally different moment and with a different set of stakes. The security architect's defining challenge is the design review, where someone in the room argues that an obscurity measure makes an additional real security control unnecessary. The product team proposing the admin portal at the hidden URL genuinely believes that the URL's unguessability is a security control. They are not being negligent. They are applying a reasonable intuition that a door nobody can find is a door nobody can open. The architect's job is to articulate precisely and without condescension why this intuition fails over the time horizons relevant to organizational security. The argument the architect makes is not that the hidden URL provides nothing. It does provide something, as acknowledged earlier. The argument is about the failure mode when the secret is compromised. Authentication and IP allow listing fail gracefully. An attacker who obtains the URL but not the valid MFA token and not access to the corporate VPN cannot access the portal. The hidden URL alone fails catastrophically. An attacker who obtains the URL has everything they need. The failure mode of real security controls is that an attacker must obtain multiple independent factors, each of which is hard to obtain. The failure mode of obscurity is that an attacker must obtain a single piece of information, which has historically proven obtainable. The architect who frames the choice this way, what does your security look like after the secret leaks, and is it acceptable, is asking the question that clarifies why the real controls are necessary. The detection engineer's relationship with this principle is inverted in an instructive way. The architect worries about the defender's obscurity being defeated by an attacker. The detection engineer worries about the attacker's obscurity being used to defeat the defender. Attackers use a range of obscurity techniques to make their activity blend into legitimate traffic, encoding commands in base 64 to avoid string-based detection, communicating over standard ports and protocols to avoid network anomaly detection, using legitimate administrative tools to perform malicious actions so that process-level detection sees only expected software, timing their activity to coincide with periods of legitimate high activity so that volume-based anomaly detection does not. Trigger. The detection engineer's response to attacker obscurity is behavioral detection rather than signature detection. A YRA rule that matches a specific encoded string is defeated by changing the encoding. A detection rule that identifies the behavior, a process that reads a file, encodes its content using a transformation function, and writes the encoded content to a network socket, is harder to defeat because the behavior is the mechanism, and changing the mechanism changes the malware's functionality. The shift from signature-based to behavior-based detection is the detection engineering response to the attacker's use of obscurity. It is also, notably, a demonstration of Kirchhoff's principle applied in reverse. The attacker's security through obscurity model, if the encoding is not recognized, the detection fails, is defeated by a detection model that does not depend on recognizing the specific encoding. It recognizes the behavior regardless of how the content is encoded. The threat researchers encounter with this principle is in the lab, staring at a binary that has been designed to be obscure. The binary is packed, encoded, and possibly checking for the presence of a sandbox environment before executing its actual payload. The researcher's task is to defeat the attacker's obscurity without knowing in advance what the attacker has done. This is reverse engineering as an adversarial process. The attacker has applied obscurity as a defense, and the researcher is penetrating that defense. The research process begins with what can be observed without executing the binary: file type, section layout, entropy, imported functions. High entropy in the code section suggests packing or encryption. A small number of imported functions. Many packers import only the functions needed to unpack and then resolve additional imports dynamically at runtime, is consistent with a packed binary. The tool used to pack the binary may be identifiable from a fingerprint in the binary structure, and a known packer can often be stripped with existing tools. If the packer is custom, the researcher executes the binary in a debugger and sets breakpoints at the memory allocation and write operations that the packer will need to perform to unpack the payload, then dumps the memory after unpacking is complete. The unpacked payload can then be analyzed as a conventional binary. This process works because the attacker's obscurity, the packing and encoding, does not change the functional requirements of what the malware must do. It must unpack itself. It must resolve its dependencies. It must make system calls. Each of these requirements creates an observable artifact that the researcher can target. The obscurity adds effort, not impossibility. Enough effort is a meaningful deterrent for casual analysis, which may be all the attacker needs. Most automated sandbox analysis runs for a limited time and may not trigger payloads that wait for specific conditions. But it is not a defense against a determined researcher with the time and tools to follow the execution chain wherever it leads. Kirchhoff's principle, from the defender's side, build systems that are secure even when an attacker knows how they work. From the attacker's side, demonstrated empirically by every malware sample a researcher has successfully analyzed. Assume your obscurity will eventually be defeated and plan accordingly. Case scenario: the admin portal, the forum post, and the disgruntled employee. You are the security lead at a mid-sized technology company. The company operates an internal administration portal used by the IT team for managing user accounts, provisioning systems, and accessing configuration management tools. The portal is hosted at a URL that includes a 32-character random string, company.com/9FB2-3901-7C22-8B3-49D7-2C90. The IT manager's position, which has been consistent for 3 years, is that the URL's complexity makes the portal effectively secure. No automated scanner will find it, and no attacker who does not already know the URL can access it. You are preparing for a security review and identify 3 concerns with this position. The first is that the URL is not actually secret. It appears in browser history on every IT team member's workstation, in the internal IT wiki, in onboarding documentation for new IT staff, in help tickets where IT staff have included the URL for reference, and in at least one email chain that was CC'd to a project manager outside the IT team. The second is that the portal has no authentication beyond the URL. It presents a login form with username and password, but no MFA, and it is accessible from any IP address, including mobile devices on external networks. The third is that there is no logging of access attempts beyond the web server's access log, which is not being monitored. You present these concerns at a planning meeting and encounter the expected resistance. The URL is long and random. It has never been compromised, and adding MFA will create friction for the IT team that logs into the portal multiple times per day. The IT manager's argument is coherent given their mental model of the portal's security. Your argument is about what happens when that mental model is wrong, specifically what the security posture looks like on the day the URL becomes known outside the organization. Your remediation proposal has 3 components. The first is MFA for all access to the portal, implemented using the organization's existing MFA platform, which the IT team already uses for VPN access. The specific configuration for the portal uses a risk-based step-up. If the user is accessing from a managed device on the corporate network, the MFA prompt appears once at the start of the working day, and the session persists for 8 hours. If the user is accessing from an external network or an unmanaged device, the MFA prompt appears at every login. This configuration addresses the friction objection by minimizing the prompt frequency for the most common use case, while maintaining full enforcement for the higher-risk cases. The second component is IP allow listing that restricts access to the portal to the corporate network's egress IP ranges and the VPN's IP range. This means that the portal is not reachable from arbitrary internet addresses regardless of whether the URL is known. An attacker who obtains the URL but is not connected to the corporate network or VPN cannot load the portal's login page. The allow listing is enforced at the network layer, a firewall rule or a cloud security group, rather than at the application layer, so that the application itself is not reachable from disallowed addresses and cannot be targeted for application layer attacks, even if its URL is known. The third component is monitoring. An alerting rule is configured on the web server access log and the firewall deny log to fire on any access attempt to the portal URL from an address outside the allow list. Any such attempt represents either a misconfigured internal tool that is attempting to reach the portal from an unexpected network, or an attacker who has obtained the URL and is attempting to access the portal from outside the corporate network. Either case warrants investigation. A secondary alerting rule fires on any authentication failure rate above a threshold on the portal's login form to detect credential stuffing attacks. You present the proposal and the IT manager agrees to the implementation on the condition that the risk-based MFA configuration is in place before rollout. The friction concern was the primary objection, and the risk-based configuration addresses it. You retain the hidden URL in the implementation, not because it provides security, but because it does provide some friction for automated scanners, and there is no cost to keeping it. You document explicitly that the URL's obscurity is supplementary friction, not a security control, and that the security of the portal depends on the MFA and IP allow listing. Approximately 6 months after the implementation, a former IT team member who departed under difficult circumstances posts the portal URL on a public forum along with the username format used by the company. Within 40 minutes, the monitoring alert fires on 14 connection attempts from external addresses, all receiving firewall denies. The portal's content is never accessible to any of the attempts. The MFA token and the VPN access that the former employee did not have proved to be the actual security of the system, exactly as the design intended. The post-incident review produces 2 additional actions. The first is a review of all accounts belonging to former employees on systems with elevated access to verify that deprovisioning was complete. The second is a document policy that instructs the IT team not to include the portal URL in help tickets that are visible to non-IT staff. A reduction in the number of places where the URL is distributed, not because the URL is the security, but because reducing its distribution slows future reconnaissance efforts by attackers who do not yet know it. The obscurity is maintained as friction, with clear organizational understanding that it is friction and not a control. Closing, the system that holds when the secret leaks. The practical discipline that this principle instills is a specific question asked of every proposed security measure. What does the protection look like on the day the secret is known? If the answer is that the protection is gone, the secret was the security. And secrets, over the timescales of organizational security, do not keep. They appear in browser histories, in configuration files committed to repositories, in emails forwarded to the wrong recipient, in conversations overheard in offices, in documentation produced by contractors who have since left. The secret that felt safe 3 years ago has been through 100 transmission events that nobody tracked, and the probability that every one of those transmission events preserve its confidentiality is not one. If the answer is that the protection holds even when the secret is known, because authentication and authorization and encryption are doing the actual work, and the secret was only ever making the attacker's reconnaissance slightly more expensive, then the system is built on the right foundation. The attacker who learns the port number, the URL, the internal network addressing scheme, the algorithm, who becomes, in other words, fully informed about the system's design, still cannot access what they should not access, modify what they should not modify, or read what they should not read. Because the key, the credential, the authentication factor, the thing that is genuinely hard to obtain and that cryptographic and operational discipline keeps hard to obtain, is what stands between the informed attacker and the system. Kirchhoffs wrote this in 1883 about telegraph ciphers used in wartime. The specific technology has changed completely. The principle has not changed at all. Assume the enemy knows the system. Design the system to be secure under that assumption. Everything else is a nice-to-have, not a foundation. End of session. Never rely on obscurity alone.